Section 2.13 Electronegativity and Bond Enthalpy. Electronegativity is proportional to the sum of the ionization energy and the electron affinity. En is proportional to IE plus Ea. So this is why cesium has the lowest electronegativity, because it has the lowest ionization energy, the lowest electron affinity. And also fluorine has the highest electronegativity, because fluorine has the highest ionization energy and almost the highest electron affinity. Typically, an ionic bond is formed when the two bonding atoms differ by 1.7 or more in their electronegativity values. For example, if you have hydrogen with a 2.1 electronegativity, and then oxygen, I think that's 3.5. So 3.5 minus 2.1. The difference is 1.4. It's lower than 1.7. So the usual bond is covalent bond. Similarly, if you look at carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. The difference is only 0.4. So it's not an ionic bond, it's a polar covalent bond between carbon and hydrogen, and between oxygen and hydrogen. But if you compare sodium and chlorine, their electronegativity differ by more than 1.7. Therefore, you have an ionic compound. However, there are often exceptions. For example, hydrogen fluoride, the electronegativity of hydrogen is 2.1, fluorine 4.0. They differ by 1.9. Yet, hydrogen fluoride is usually considered a polar covalent molecule. Another example is aluminum oxide. I think this aluminum oxide has a difference in the electronegativity lower than 1.7, but yet it's a ionic compound. Alright, so typically, if you have an ionic bond, the difference between the electronegativity values of the atoms differ by 1.7 or more, but there are exceptions. What if the difference is between 0.1 and 1.7? Usually it's a polar covalent bond. If you have a homonuclear diatomic molecule like O2N2H2, then it's a non-polar bond, because the two atoms have the same values of electronegativity. But in ozone, pay attention here, this is a polar molecule. Although all three atoms are oxygen atoms, but look, the central oxygen atom has a +1 formal charge. The other two oxygen atoms each has a -0.5 charge. So it's a polar bond between the center oxygen atom and each of the two other oxygen atoms. This diagram shows you how to determine whether a bond is a metallic bond, covalent bond, ionic bond. So over here, if you have metal atoms, they typically have low electronegativity, so along this side. So again, this is just the electronegativity of the atom. So along this side, alright, let's say you have cesium bonded to cesium, and then it's a metallic bond. And then maybe sodium is somewhere here. Alright, so between sodium and sodium, you have a metallic bond. Alright, now between fluorine and fluorine, you have a covalent bond. Oxygen has a 3.5 electronegativity. So oxygen is here, nitrogen is here, carbon is here. Those are covalent bonds. Hydrogen, I think, is here. Two hydrogen atoms form a covalent bond. Now look at the vertical axis. That's the difference between the values of electronegativity of the two atoms. Now let's look at this example, cesium fluoride. I think fluoride is 4.0, cesium is roughly 0.5, the difference is 3.5, so huge difference. When the difference is large, you have ionic bond. So over here you have ionic bond. All right. Now between silicon and oxygen, well, the difference is small, and then, well, I think we have a covalent bond here. Oh, by the way, this chimene is the average value of the two atoms that form a bond. So this is average of the values of silicon and oxygen. So the average is 2.8 over here. All right, and the average between magnesium and oxygen is roughly 2.5. I know oxygen is 3.5, then magnesium is 1.5. So the average is the average of 1.5 for magnesium to 3.5 for oxygen. So the average electronegativity of MgO is 2.5 right here. What's the difference? Well, the difference is 3.5 minus 1.5, that's 2. So roughly 2 here. This is the difference too. So again, this diagram helps you to determine the nature of the bond. Alright, so if the difference is small, so on the lower end, it's a covalent bond. If the difference is large, it's more like an ionic bond. Alright? And when the difference is small, and also the electronegativity of both atoms are small, that means you have two metals, and that's a metallic bond. The red region, we don't know. So it can be ionic, it can be covalent, it can be metallic. It's not a very clear area. Finally, the oxidation numbers. We need to know the electronegativity to determine the oxidation numbers in a molecule. For example, in methane, so you have one carbon, you have 4 hydrogen atoms. To determine the oxidation numbers, you need to assign all bonding electrons to one of the 2 participating atoms. So you have 8 bonding electrons in methane. You need to either assign the 8 bonding electrons all to carbon, or 2 electrons for each hydrogen. So in CH4, how do we assign the electrons? We compare the electronegativity. The one with higher electronegativity gets all the electrons. So in CH4, carbon gets all 8 electrons. In that case, carbon has an oxidation number of -4. Hydrogen has a +1 oxidation number. Now let's look at water. It's simpler. Again, we give all the bonding electrons to oxygen. Now oxygen has 8 valence electrons. Well, supposedly a free oxygen atom should have 6. So 2 more than a free atom. That means the oxidation number of oxygen is -2. Again, hydrogen +1. However, if you have a sodium hydride, the sodium has lower EN value, hydrogen is more electronegative. So this time, when we form a bond between sodium and hydrogen, you give all the electrons to the hydrogen. And then the oxidation number of hydrogen is -1, the oxidation number of sodium is +1. Now a few more examples. What if you have hydrogen fluoride? Well, again, fluorine has a higher electronegativity, so you give the 2 bonding electrons to fluorine. And then fluorine is -1, hydrogen is +1. And now we have some rules over here. The sum of the oxidation numbers of all atoms should be equal to its total charge. So if you have a large molecule, let's say sucrose, and then the sum of the oxidation numbers of all atoms should be 0, because I know a sucrose molecule is neutral. Phosphate PO43- has 3- charges, and therefore the oxidation numbers of this phosphorus and the 4 oxygen atoms together should be -3. All right. For atoms in their elemental form, that's 0. So in O2, N2, H2, a piece of metal such as sodium, the oxidation number is 0. All right, bromine 2, that's an element, so 0. For atom in group 1 plus 1, so that's hydrogen, lithium, sodium, potassium, rubidium, etc. Atom in group 2, beryllium, magnesium, calcium, etc., etc. All right. So group 13, so you have boron, aluminum, gallium, except boron here, because boron sometimes gets electrons rather than lose electrons. So for aluminum, it's definitely plus 3. All right. Group 14, carbon, silicon. Carbon, silicon, they can be plus 4 or negative 4. All right. But then for germanium, it's usually plus 4. All right. So there are exceptions. For hydrogen, usually it's plus 1. Sometimes it's minus 1 if hydrogen is forming a bond with metals. For fluorine, it's always negative 1. For oxygen, it's almost always negative 2 unless it's combined with fluorine. In OF2, so you have oxygen difluoride. Then the oxidation number for fluorine is still negative 1. Oxygen plus 2. There are exceptions. When you have this peroxide, it's negative 1. In H2O2, the oxidation number for oxygen is also negative 1. Superoxide, again, overall there's a negative 1 charge. You need to give this negative 1 charge to 2 oxygen atoms, so you have negative 1/2. For halogens, usually it's negative 1, but if you have fluorine chloride, the fluorine is negative 1, the chlorine is plus 1. Okay, the name should be chlorine fluoride. And then you can have like iodine bromide, iodine chloride, bromine chloride. And then in these cases, the more electron negative halogen has a negative 1 oxidation number. The hydrogen with a lower electron negativity has a plus 1 oxidation number. So now one more example. Let's look at a ionic compound. How about sodium carbonate? Sodium carbonate, overall it's neutral. Sodium is plus 1. Carbon is plus 4. Oxygen is negative 2. And then we need to look at the number of atoms. You have sodium carbonate. You have 2 sodium, 1 carbon, and you have 3 oxygen. So 2 sodium, 2 times plus 1. 1 carbon, 1 times plus 4. Oxygen, 3 times negative 2. So overall, you have plus 2, plus 4, minus 6. That's 0. So overall, if you have sodium carbonate, the sum of the oxidation numbers of sodium, carbon, and oxygen is 0. Again, it's 2 plus 4 minus 6 is 0. And similarly, you can determine the oxidation numbers for almost all molecules.